different industries prefer some CAD softwares to the other. The most, well, I say, not just popular, but the most sought after CAD software is usually SolidWorks. Almost every job description for mechanical design you'd see would require that you have proficiency in SolidWorks. But then some other CAD softwares are particular to some industries, like civil engineering industries uses Revit. That's this one. They use Revit for their computer designs, even AutoCAD. So civil engineering industries use Revit and AutoCAD. Robotics industries, they use SolidWorks. They also use Fusion. Then aerospace industries mostly use SolidWorks and CATIA. Some mechanical companies that do mechanical design full-time on scale, they use Inventor and SolidWorks mostly. Then Onshape is used for cloud collaboration. It's also a CAD software. Siemens NX is a CAD software that helps you to do CAD and also analysis. So the big question, do you really need to learn CAD? This is more like a question that is always asked because I mean, everyone is more like, as a robotics engineer, do you need to learn CAD? But the truth is that not everyone needs to learn CAD unless you are going into the hardware side of things. And then unless you also want to understand in details the structures, the mechanical structures of the robots, how it's being aligned, and you're designing from scratch. That's when you need CAD. So basically, when you then analyze that, oh, I need to design something, I need to design your robot from scratch, then you then decide to do your drafting, and then you begin to, after drafting, you begin to design on CAD software. So you only learn CAD when you're looking towards careers like design for robotics, maybe mechanical design engineering, or robotics design, or robotics hardware. Yeah, that's when you actually need CAD. So when is CAD used in robotics? So prior to building any cool robot, not just about being cool, a functional robot, you need CAD before you start building a robot. After you decided on what the robot is going to do and the function of that robot, you now decide about the structure, and that's where CAD comes in. So before building your robot, you have to use CAD to analyze the robot, to design the robot, to create a model of the robot, and know how the robot is going to look like, optimize the design in case of errors or maybe changes in structure that you'd like to place. Also, CAD is used in simulation and testing. So when you're done designing your robots, you can now use those CAD models for the robots to simulate the robot and know what the robot is going to look like, more like model it and test out the functionality. Probably if it's a robot that is movable, that has movable joints, maybe a robot arm, you can use CAD to simulate the motion of the robot arm. Also, when integrating hardware and software, CAD is used during iteration and redesign, and also, most importantly, before manufacturing and deployment, because you're building a robot from scratch with emphasis on that. You definitely have to design and design for manufacturing, because you're not just designing because you want to ensure aesthetics. While aesthetics is a plus, you have to ensure that the robot is manufacturable. So CAD is used to make every precision intact before manufacturing and deployment. So the why for CAD in robotics. CAD helps you to eliminate errors at the barest minimum. It ensures that all the tolerances and fits are properly checked, and all the movable parts have proper alignment. It ensures weight and space optimization, what sensors are going to be on your robot, what components are going to be interfaced in these robots, how is it going to be aligned, are the tires supposed to be opposite each other, where are the motors going to be placed, those kind of things. So CAD also helps you to have simulation ready models where you're able to use CAD to design models that are ready for simulation. Also, it helps for faster iteration, reduced failures, like I said, and you can collaborate on CAD, unlike doing drafting on paper with a fellow engineer. You can collaborate on the cloud platform of CAD, where you can invite someone to your team and both of you can iterate and design together. So how is CAD used in robotics? So first of all, if you've now decided that you want to design your robot on CAD, first you need to analyze what the robot has to do. You then determine the parts of that robot. Now you begin to design each of the parts. After designing the parts, you then assemble them. As you're assembling them, you ensure that they are in proper alignment and the different parts are placed where they're supposed to be. Then after that, you define your joints and motion. After defining those parts of the robot, you export your CAD files in step file format or an STL file format. These are kind of universally accepted formats for exporting CAD files for either production or for simulation. So now for robots, you don't just export the CAD file and then send out for production. You have to like simulate. So now for you to simulate, you need to convert these files to a robot description format, VRDF files. VRDF stands for Unified Robot Description Format, which is more like an XML-based file in ROS that helps you to know the physical structure of your robot and be able to simulate it. So after you converted your file, you then simulate on Gazebo, fabricate, assemble the robots, then the other things can now come in place. You're sure that your robot is functional and you've been able to simulate your robot, and then you then go hands-on. So when CAD is not necessary, to be honest, it's not every time you need CAD, especially when you're doing simpler tasks, like you're prototyping something simple or you're just exploring your ideas. You're not yet sure if you're actually going to do it, like you're actually going to produce the robots in real time. And it's just maybe an idea or concept. Also, when you're working on very simple projects, let's say you want to build an obstacle avoidance robot and you know that it's something you can easily get an off-the-shelf part in the sense that you can buy the parts on the market or order them and it's cheaper, then CAD is not necessary at that point, because when you're designing something or when you're building a project, you have to save time to both optimize cost and improve efficiency. So basically, you don't have to like go the hardest route all the time, because having to design from scratch, start printing or fabricating if it's maybe sheet metal, it's going to take a whole lot of time when it's something that you can use off-the-shelf parts to save your time and also money too. So, like I said, when time and resources are very limited, you don't need to use CAD. I'll use this for example. This is a Scuttlebot. It's a mobile robot used for navigation. So this robot was built for logistics, navigation, right? And also to be able to carry a payload. Now, the only reason why you're seeing these sketches and model here was because I modeled this to be able to analyze the amount of payload that these robots can carry. And why is the robot carrying a payload? Because it was defined for the function of the robot, one. Number two, the material for the robot is something that can at least carry a load. This is an aluminum extrusion, right? So basically, I had to like model it to understand and analyze the amount of load it can carry. Now, imagine that I wanted to build this robot from scratch and I decide that I have to design everything on CAD before going to manufacture. Like I design everything, even the sensor plates, everything, the corner pieces. It's not really going to make sense. On the other hand, it makes sense because I want to learn, one. But then on the other hand, too, it's going to waste a lot of time. So it's actually better to use off-the-shelf products, because this robot was assembled using off-the-shelf parts. And it actually saved a lot of time instead of trying to do everything from scratch. So CAD versus mechanical design. Now, these are two concepts that are usually misinterpreted, or will I say interchanged? Yes, because a lot of people feel like when they're learning CAD, they're also doing mechanical design. While some people feel like mechanical design is CAD itself. But then mechanical design is actually the engineering thinking. It's the decisions you make to ensure that your robot is functional, right? It's about you defining how your robot works, the strength of your robot, the material type, the forces that are propelled on your robot. Every single component on your robot carries a little amount, like it carries weight, no matter how little it is. Even your sensors can carry like 0.05 grams of weight, right? So all of these things in mechanical design, especially when you're designing for a particular function, you need to put all of this in check. So on the other hand, CAD just shows you how your robot looks like. It just gives you a visual representation of your robot and then validates your design to like, oh, I have done this and okay, this looks good. CAD is more like a tool set, while mechanical design is actually all the decisions you make, how you make your robot functional, and how it actually works. So the key aspects of CAD. Now, CAD involves bringing different concepts together, bringing different skills together to ensure that your design comes to life. So we have technical drafting and drawing. This is where you do your 2D sketches. You use lines, shapes to bring your design to life. Then we also have 3D modeling. There are different aspects of 3D modeling. We have parametric, part modeling, assembly modeling. We also have mesh modeling, sheet modeling, right? So it all depends on what you're doing, what you're designing for, and the function of what you're designing. So we have rendering. Rendering is more like a stage after your design is completed, and then you have to give your design a picture-like look, like looks like, let's say, you have to give it a look that it's like that is in real time, more like giving a real visual representation of what you've designed. Now we also have geometric dimensioning and tolerancing. So this is more like a key skill in CAD. Even most job descriptions you see would require that you have GD and T skills, because this is how they'll just write GD and T. So it's more like a skill that needs you to understand dimensions and tolerances, basically the holes and the holes, the placement, the orientation of those holes. Are you able to give a tolerance of 5 millimeters? Are you able to even denote descriptions of tolerancing? Like if you're to see symbols of tolerancing, be able to decode it, and when you're manufacturing, you're able to apply that. So it's about giving design objects and movable parts, mating parts allowance to ensure manufacturability, most importantly, because there's every tendency that you design a robot, and let me say maybe a robot arm, and then the robot arm has grippers, and you did not place enough tolerance to allow the grippers to open up to a good amount of space that would be able to grab whatever it is that the gripper would grab. So it gives a problem. So all this tolerancing helps you to ensure that even when they manufacture that robot or that product, there is not going to be an issue. There's still going to be manufacturability, very feasible, right? Then also file management, where you're able to know what file formats to export, how you're able to manage your files, and also have cloud collaborations. Now, the key aspect of mechanical design. Now, mechanical design involves all of the things that make your robot functional, like I said, the mechanisms, the kinematics, material selection. Why are you using aluminium? Why not galvanized steel? Is this material going to serve this purpose? Let me say, for example, you're building an underwater robot, or maybe, yeah, let me use an underwater robot. Now, the material you're using for the robot, can it be resistant to corrosion? Why are you using this material? Like, what material options do you have? Then we also have tolerance and fits. We also have design for manufacturing and assembly. Then even cost estimation, I didn't include that here, whereby you're able to ensure that the best materials you're able to get also balances the cost, because no matter what, as you're manufacturing, you're optimizing cost and most importantly, time. So another thing is system level thinking, where you're able to have proper idea on bringing things together, ensuring that all the parts are integrated properly. Did I? Oh, I think I skipped something. Okay, yeah. So how do you explore CAD as a beginner? So as a beginner, you would want to like ensure that you learn the proper things at the right time, right? So when you learn CAD, also understand the most important things, which is the mechanical design thinking. This is where your basic engineering knowledge comes to play. You'll be able to understand at least kinematic, your statics and dynamics. This is also where they come to play. Understanding forces that react on a body, free body diagrams, all those things, your material science, engineering economics, because when you're designing, or maybe let me say a startup gives you a design to carry out, all of these things will be required of you. You cannot design something without having to understand the basic concepts. So another thing, after that, you have to start with 2D drafting, which is something I normally recommend, because you need to understand how to create geometries. You need to understand how to sketch shapes out, because the 2D sketches form the basis of the models. So if you want to model anything or design anything and you don't understand how you can even start to sketch to go about your model, then it's a problem. That's why I always advise someone to do a lot of 2D drafting exercises, so that you can be able to master how to go about 2D drafting of different shapes and geometries. So another one has to be following up with 3D modeling. When you're very convenient with learning 2D drafting, you move to 3D modeling. There you can now start to model things in 3D form. You can start with simple parts, mechanical designs, enclosures. It can be something small, but at least you're learning. They're not just the 3D modeling, but assembly. If you start with small parts, right, you can now learn how to assemble things, maybe enclosure of a Raspberry Pi, design the base, design the inner parts, the top enclosure, learn how to assemble both of them together with the Raspberry Pi too. So another thing also is to focus on understanding functions and not aesthetic. So many people feel like that is just about how it looks like, but no, it's about the function you give. So as someone learning CAD for robotics, it's very ideal to connect your CAD models to a real robot use case. I mean, you might be wanting to build a portfolio for design for robotics, and then designing stuff related to robotics will actually give an edge. So the final thing I will have to say here on exploring CAD as a beginner has to be to practice. To be very honest, practicing is key. What is that person? Okay. To be very honest, practicing is key. If you don't practice, there's every tendency that you would actually lose some kind of, not just focus, but you will not be able to learn faster. So when you practice, you're able to like navigate the platform or the software better. You're able to like design and even get better with using tools and features in the CAD software. So this is where I talked about the learning process, right? So this is the 2D draft of a wrench, and this is the 3D model of the wrench. Now, this is to show you that in CAD, you don't just use maybe just like, I don't know what software to use, but you don't trace out the outline of anything to create a draft or to start designing something. You have to use shapes, lines to form the geometries. That's why it's very important that you learn how to do 2D drafting, so that before you're able to create a model, you're able to know what shapes you combine, what line types. Is it an ellipse? Are you trying to use a circle or anything to combine to form a model? So I thought it's wise to recommend CAD-based robotics projects for people that may want to like start. So you can design mounting brackets for motors and sensors. I know people design mounting brackets for LiDARs and even for ultrasonic sensors. Also, you can design a differential drive robot chassis. Something like this one, something simple, something complex, depending on how how far you want it, right? Because some people don't want something stressing, some people want to go all in, right? You can design a robot arm joint, enclosures for boards, even a drone arm, drone propellers even. You can just play around and try to like learn stuff while you're understanding what and why it works. So okay, these are basic things, like just sample things you can design. This is like a bracket for a DC motor. This is just an aluminum extrusion, the one I modeled for the test I wanted to do. This is a corner piece for this extrusion, while this is an enclosure for a water level indicator. Now, this is supposed to be a chassis for a self-balancing robot. I purposely put this here to analyze on something. Now, you see how bare this design is. You could actually know that this was one of the earliest designs I did. So on a normal, you could see this design and be like, okay, it looks at least good. But here you could see that there are some things missing, right? There's no holes for sensor placement, nothing. So this is just a basic design. But I mean, as a beginner, you can try your hands on anything basic. So we come to computer-aided design in advanced robotics. Now, in advanced robotics, CAD is very helpful for the full robot system modeling. It helps you to analyze the joints, the links of the robots. Links are basically like the parts of the robot's arms, the how will I put this? The the distance between the between each joint. That's what a link means. So that is also used for balancing the weight and then center mass control to just ensure that when you're simulating, there's really no issues. You're actually getting what you want. So basically, it's not just about the parts, because you need to ensure that the accuracy is very, like the accuracy is achieved. And then also in advanced robotics, CAD helps you to integrate control, especially when you're simulating. So computer aided design in robot description. So robot software cannot directly understand CAD files, right? So because of this, the CAD geometry has to be simplified and translated into robot description, especially in file formats like QRDF or SDF. I've explained what QRDF means earlier on. So these these URDF files, this robot description, they define the links and joints of this robot prior to simulation. That's before simulation. They also define the joint limits, the axis, and all of that. So it helps you to understand different aspects of the robot, the degrees of freedom, and where you need to like implement corrections, probably in the file when you're writing the robot description, because it's more like a file format that you have to write out. So CAD basically helps you to use the models that's already designed in CAD software for the robot description. You're not actually doing the CAD while you're doing robot description. You're using already designed CAD models for robot description. So CAD is simulation. Now, we already know that simulation helps you to foresee or analyze your robot and the performance and how it can actually function in your software, not in real life at this point, because it's on your system. You are seeing it. You can simulate a robot, and at the end, something happens as you're building the hardware, right? So that enables you to simulate after you're done with writing your robot description. Simulation softwares are usually called physics engines. They help you to detect when the movable parts are aligned or not aligned, if there's a collision or misalignment, if they are moving properly, and then it helps you to test control before you now go to hardware. So how does CAD help you in simulation? The same thing with robot description. You're already using the CAD models that you design on CAD. So instead of trying to do something new, you're now importing those models from the file format you've converted it to, and then using it in simulation. So these are different simulators. This is Gazebo, Webot, and NVIDIA Isaac. I don't know if you are familiar with this, but if you don't know about them, maybe you could check them out. But they are simulators. So this is a basic CAD to simulation workflow. At first, you design your model on CAD software. Then you proceed to converting it to a robot readable file, like for your robot description. Then you simulate. So CAD and digital twins in robotics. Okay, digital twins are more like the virtual replica of a physical robot, right? So CAD helps to provide the geometry and physical structure that brings about the possibility of digital twins, where you're able to replicate an already existing robot in CAD, and then you're able to simulate it to perform similar functions that already existing robot is performing. Take for example the Fanuc robotic arm or the Kuka robotic arm. I could just model the robot arm exactly as it is, then convert it to a URDF file, simulate and carry out certain functions and control algorithms based on what I want to do with it. So digital twins enable the use of CAD for optimizing performance, to check out for failures just in case, and to test changes in a safe way, because it's actually better to simulate and understand where there are errors or where there are no errors, so that instead of deploying or bringing up everything in hardware, which is even more expensive, you have to go the safe route. So this is where I talk about my journey in building AutoBot. Now, AutoBot is a mobile robot for obstacle avoidance and four-way tracking. So I built AutoBot because I wanted to learn more. It was an old project, by the way. So I wanted to learn more and I wanted to stretch myself a bit. There were two major reasons, right? So aside the fact that I did the hands-on building, I went extra mile to design a robot from scratch, more like I reverse engineered the bot and designed from scratch. So how did I build it? At first, I had to analyze the most important, or let's say the major part of this robot, which is the chassis, the motors, and then the sensors. I then know that, oh, I have three parts. Now, I began with the 2D drafting, which is this. When I got the chassis, I had to sit down and analyze this chassis. I found out that there was symmetry. If you notice, there's a red line here, right? So there's a symmetric resemblance on the whole positionings, both at the upper part and the lower part of this red line. So I had to like take out my measurements, ensure that there was proper spatial orientation of these holes, because the holes were necessary for mounting sensors and then standoffs. Standoffs, I'll show you what standoffs are. They are more like spacers for the two chassis. So after my 2D drafting and checking out for the correction, dimensioning and everything, I then went on to do the 3D model of the chassis. So this is the 3D model of the chassis, right? Then I started assembling things. Now, I moved on to assembling instead of trying to design other parts. Why? Because I had to like save time for more important things. You don't really have to like reinvent the wheel all the time. There are some already existing models of standard parts that you can actually use online when you want. You can actually import from online when you want to design a major system that requires so many components. So you can get those models on GrabCAD, even Fusion 360 and SolidWorks. They have libraries for standard parts that have measurements that are standard, like they are organized internationally by engineers, that this device has this measurement, it has to use this screw type, whether it's M3 screw or this or whatever it is. Just models that are already standard. So these DC motors with the tires, they were already standard models. So I had to import them. Now, after importing them and placing them, ensuring that they were properly placed, I used standoffs, right? So Fusion 360 has a library for importing screws, bolts, nuts, standoffs. They made like all these major tools you can use in joining parts and fastening parts together. So that was where I got the standoffs from. Then assembled the second chassis, and then finally imported other components and put in screws and all of that and fix all of them together. So making design choices in CAD. Hmm. Basically, I will start with my design choices for AdBot. Now, aside the fact that I wanted to go extra mile to ensure that I designed the robots, right? I had to make certain design choices. When it comes to material selection, I had to understand that this is a chassis that I can 3D print, right? I have to use the right material for it. I also checked out for the symmetry, like I talked about. I ensured the different parts were aligned, and also even on the chassis, proper orientation of the holes, and then giving tolerance where necessary. So these are kind of design choices you can make to ensure that there is manufacturability of your design. Now, some other design choices include material thickness, joint type, even orientation of your design, your modeling type, part count and assembly method. How many parts does your design have? What method are you using to assemble them? The geometry and dimension. So these are design choices made in CAD to ensure that your design is not just an anyhow design, but something that is going to be manufacturable. So talking about the design trade-offs in robotics, in real life, your robot design is not just about the aesthetics. I'll still repeat this. You need to choose between options. And not this does not just it's not just reduced to robot design, but any design at all. So you have to choose between options and weigh certain criteria before you design. Now, you can't have everything perfect at once. You need to understand the critical maybe like things like cost and performance, even the development of the robot or of your product. How fast can you be able to ensure that you meet up production in time? All those things. So you need to choose between certain parameters to ensure that your modeling is flexible, your design is actually manufacturable. That is very key. Now, when it comes to weight and strength, take for example, if you make a robot very strong with heavy materials, it becomes too heavy to move easily, right? And now, on the other hand, if you make it light, it may not be strong enough. So, in everything, you need to ensure that there's at least a balance. While you're weighing out this option, you should also ensure that the other one is checked out. So you don't like strike off one thing and then it leads to a failure. Also, when it comes to cost and performance, sometimes you may want the best sensors and the motors that can carry out something. And then those sensors and motors can be very expensive. But then sometimes now when you pick a cheaper part, right, they still get the job done. Like when you kind of replace it with sensors and motors that are not so expensive, most times they get the job done. Also, on the other hand, if you look at it on the other way, sometimes the best performing robots that are very expensive, if you reduce the cost and bring up parts or components that are not so expensive, you may even lose performance. So you need to actually understand what you want to do and then weigh your options properly before making decisions. Other trade-offs include modeling approach, sustainability. Modeling approach, are you using parametric modeling or direct modeling? Parametric modeling is a kind of modeling whereby you have to define all your parameters, your length, your diameters, your thickness from the start of the design, meaning that it's kind of tougher to change it back when there's a mistake. While direct modeling, as you're modeling, you can change errors on the go, and then the shape of the 3D model will still be intact. So it all depends. You need to make certain choices when you're designing, not just for robotics, but for product development. So opportunities in design for robotics. These are like opportunities I normally see and you could find as well when it comes to design for robotics. So we have mechanical design engineer. We also have robotics hardware engineering, mechanical engineering, and product design engineering. Of which product design engineering, some people really put it as product development engineering. So it all depends. So we are coming to the end. And in everything, I would want you to understand that your design connects your ideas to reality because it's actually beautiful to see your ideas come to life as you design. Then also CAD enables you to foresee your design and visualize them, how they look and how they are supposed to function. System and design thinking matters. And also engineering is responsibility. You're supposed to give out value and ensure functionality of whatever thing you're building. In everything that is discussed here today, I would want you to really understand that mechanical design and computer-aided design, they are related, but they are not the same. Mechanical design gives you engineering judgment, helps you to apply proper decision. CAD gives you precision and speed, right? It helps you to visualize your design. And also, while robotics demands both of them, you should also know that a good design has to balance trade-offs. So, thank you for listening. I'll be happy to take your questions now.
Okay, so before the questions, I want to give we'll have the Q&A at the end of the session. I want to talk about CAD from a robotics perspective. Like how would I put from a software perspective, how we interact with CAD. Chidima, please, I'll love to share my screen.
Okay.
So in Chidima's example, she is at the, I would say, the preliminary phase of a project. A project starts, or a robotics project is about to start. We are usually not the first people that is involved. They consult robotics engineers that do mechanics and things like that and say, okay, I want a car like this. Because most of the times the client doesn't really, except the client has a reference, the client just knows the function he or she is looking for. And then it's left for a mechanical designer or a robotics mechanical designer to put those things together. Now I would show you how it is on our side. After Chidima and her team, they've done the card, they've done everything. You know, there were 3 cycles that she showed, from SolidWorks or CAD, where you get the whatever format of file, OBJ, step, whatever, to URDF, and from URDF to simulation. So she's at the first 2 points, and I'm at the last 2 points. So at the center, that URDF part is where we sort of intersect. And she has showed you how the design is. You can see her sketches, and that's something we're familiar with. So I want to show the other side of the picture. So I will be doing this with a repository. This was the repository we used last year. If you can see my screen, I'll make it a bit bigger. Sorry about that. I think it's here. So this was the repository we used. And while she was, I had something else I wanted to show, but while she was talking, she focused about, she talked about Franca arm and Fanuc. And that's happened to be something we also worked with last year. Last year we worked with over like 12 different robots. So this is what happens. When Chidima and her team, they've done their design and everything looks okay, they send us 2 things. The first thing they send, let's look at the Fanuc. They send us STL files, which looks like this, and I'll open them shortly. And then they send us the final results, and then these data sheets. And what they want is, they are telling us that, okay, we've done our design. This is what the robot is going to look like, at least the skeletal design. This is what we want it to be. This design does not involve electrical, does not involve any of those things yet, right? This is just the first phase. And they send us, this is from the rendered picture, probably from SolidWorks or wherever. So this is what we get. But we don't use the whole file. As a matter of fact, we don't need the assembly, because Chidima would do the assembly, and we don't need any of that. So what we do is we take something like this. If you look at this, this looks like just one part. This, on the other hand, looks like another part. We have this that looks like another part. There is a better software that helps us visualize it better. If I can pull up something real quick. So ideally, I do not interface with the GUI, with the design or anything. 2.stl. All I'm going to do is I'm trying to run it, and then I will look at it and say, okay, if this looks good to go. Most of the times, you see, this doesn't contain as much detail because we simplify the detail, because simulating things like this, if it has too much detail, it tends to be very slow. So at least I can do whatever I want to do here. I can refine the detail, I can increase more detail, whatever I want to do. So let's assume that is done. The next thing I will do is, and that was the project that the last cohort they did. I gave them all these files, and I was like, okay, you're a robotics engineer, do what robotics software engineers would do. And this is how it usually plays out. I will show you the results, not the process, the results, because the process takes a very long time. But when you are done with it, you should be able to just a minute. I think we're talking about the Fanuc arm. Was it Fanuc? It was Franca. Franca description. Franca description. Robots. Where is those robots? And then good one. Okay, so this is actually another robot, actually. But you get the idea. At the end of the day, you are supposed to end up with something that looks similar to what they are looking for. But since I started with a particular robot, let me just undo. I'll just go a step backwards. It was Fanuc, not Franca. Fanuc, URDF. Okay. So after everything is done, we have to get something similar to what they want. Now, this doesn't look as detailed or as fine or as pretty as the initial diagram they gave us, right? But that's enough for us because honestly speaking, the more the detail, the slower it takes to run. Now, the idea is since we have this robot, this is an exact digital twin. So now, what do we need to do? What do we do with things like this? You've seen those nice videos where the robot hand is just moving around and maybe welding or doing something. Before they weld, before they do anything at all in real life, we do it in simulation. Like every robot you see has gone through simulation. Why? Robots are extremely expensive. And imagine putting a robot and somehow you do not calculate the space around the robot. And then the robot runs into its environment or like swings the arm and hits something. That's like instant loss of money like on the spot. So what we do is we model both the environment, we model both the robots, and then we try to like make it work. Another thing, there was something very impressive that was done last year, and that was by two of our interns, right? So let me just show you something similar, but with a more complex kind of robot. github.com. Great sir. Okay, so this is Great Osa. Yeah, he was the one I put on the first day as the intern of the week. He's also a very great guy. This is part of a research track at the company. Just interns here. So just a moment. So it's actually taking quite a while to come up because of the amount of work that is actually in this particular. So if you actually remember, on the first day, I showed something like a robot dog, right? Something some of us must have seen. This is the modeling. You can literally move it around. They put a lot of work into this because there were so many times we're on call to get something like this done. And this is how it is in the industry, really. Now, it's very much realistic because if we actually check it properly, it doesn't collide with each other. It has limited range of motion. They took their time to implement a lot of all these things. All the joints are movable. So exactly as it is in real life, that's the way it's going to be in simulation. And it's because of this knowledge and this idea that I'm aware of that always gives me that always make me tell people you don't actually need that hardware, right? But you need an extremely high amount of software skill if you don't want to like purchase so much hardware like that. So it's just how it is. The fact if this particular one, this is the actual, this is what they are trying to model, right? And if there's something we find out, if you notice this particular front leg, this, I think it's this one. Okay, it's maybe up. Keep this, it can't go past that limit. And that's pretty much how it is. It's not going to go past that limit. So what happens is, since the people who designed the card, they know how they know the limit, they know the tolerance, they design with precision. All they need to do is just to send us the different parts and like a sheet or like a technical documentation telling us, hey, this is what it looks like from the mechanical point of view. All we do is replicate it, and from here, the next place we go to is simulation. And you might now ask, okay, in simulation, what is the idea? Now, these projects I showed you now are more like research projects, so I can't really show their simulation per se, but I can show that of I don't know if the video is going to lag, but it's already a bit slow. Okay, I can close a few things. All these things are like resource intensive, so it gets a bit overwhelming. Okay, so a particular project we had was, I don't know if you know of this Roomba, this kind of almost cleaning machine that cleans the house like automatically. You just turn it on and it goes everywhere and it cleans the house. Now, if you've ever seen one in action, they don't know the house. What they do is they have the wall, they move and then they hit the wall. Once they hit the wall, they are sensors like, okay, yeah, there is a wall there, or at least when they get close to the wall, that's if they do have ultrasonics or LiDAR. Once they get close, they now change their direction randomly. And since probability is on their side, because you just turn it on and leave it, give them like 30 minutes an hour. By the time they've gone randomly everywhere, then probabilistically speaking, they can cover the entire floor. So many times, some things are impressive, but like when you know the idea behind them, they don't sound so cool that again, because that's what now you know what they are doing. So this particular client was like, okay, you know what? I don't want something like that. I want something that knows the house. And the only way you can get something that knows the house is if that thing maps the house first. So it has a map of the house, right? You can also make it cooler for that thing to map the house at the same time be using the map it's creating as it's going on. Now, this is something that is very complicated and like this is like on the high level of things. But again, I'm explaining this because of the video I want to show and show you that, okay, this is actually how these things are applied. So on this video, hopefully it isn't slow, or But let me close a few things. At this rate, I should have like 600 terminals open at once. Okay. So let me open this with BLC. Okay, that's me. I always work with music. So basically, you start up everything. Now, this is what this gazebo that Chidima was talking about. This particular screen is gazebo. And you can see how long it actually takes to load. This is why we simplify a lot of things. Now, what just showed up is the map. Now, this is gazebo. We have the environment they wanted to work on, which is the house. And this house was not modeled by me. It was modeled by the design guys, right? I just said, okay, just give me the house. I would fit it in my simulation. Now, on the right side, you can see a map that is going to form very soon. Now, what I'm going to do is I'm actually holding a PS5 pad. That's what I was holding as of this recording. And then you can see the robots here. This Roomba, this circle disc, you see it moving. As it moves, it creates the map. Now, it's not going to collide with the walls. It's not going to, because like it's having a map as it's moving. And the good thing about this is the same way you can construct the map from the robots, you can construct a 3D world from the robots. Because like, if you notice, this map is on a 2D scale. Like you can see it drawing it on a 2D scale, moving around. All you need to do is more like extend it, project it up into 3D, and then you can. How does that work? This LiDAR scans in 2D, right? They're what's called 3D LiDARs. If you get a 3D LiDAR, then theoretically, you can be able to capture 3D geometry, right? There are samples of that, but let's just enjoy this as the map unfolds. So yeah, see the map. Now you can see the whole house has almost been mapped. We see the rooms, we see the main house, and basically. So that's like 2 weeks of work summarized in one video. So different points of different sides of robotics, different technology stack, different approach, different, all different, right? They're all different. Chidima might not have the need to do all of these. It doesn't make her less of a robotics engineer. I might not have the need. As a matter of fact, the CAD file is there's something that happened one time on one project. The CAD file was faulty, and I can fix it. Like technically, I've done CAD for 10 years, more than I've done robotics, right? But I returned the CAD file back, and I was like, they should fix it. And they're like, okay, yeah, fine, no problem. Why? I do believe that if you decided to pick something, pick that thing, and like, unless there is no choice, and I'll say, okay, yeah, fine, I will do it. It's for this reason that I create clear distinctions between what areas of field, like different areas of field. So like you know what you are, not claim that you're on the other side, like whereas you're not, right? Because you would appreciate people that actually put in that work, right? People that put in that Chidima that does the whole card and everything. As I see our LinkedIn post sometimes, and like I'll comment, I'll congratulate her, and I'll say, man, it's actually not easy. So I hope we've seen another side of robotics. I hope we've also learned one or two things. For those of us that are very good at CAD, now we've seen how CAD actually connects into robotics. We've seen how CAD moved from SolidWorks into Gazebo and into an actual industrial job, right? So right about now, we can take questions. We can take the questions you had for Chidima, the questions you had from everything. Feel free. All right, Ibrahim Hassan.
Hi, thank you very much for the presentation. I have one question regarding the mapping.
Okay.
Does the robot need to actually map like all points on the like in the house, for example? Because I feel that the house is like kind of a very wide space. So does the robot just need to move from one point to another, not necessarily mapping all the whole area, basically?
Okay, very nice question. To answer that, I would want to show you what actually maps on a robot. So you understand basically. So you see this little discs at the top, this stuff. It's called a lidar. Now what it normally do is it shoots light, like it kind of spins light outwards. Now this robot, some lidars can reach up to 12 meters, right? I want to paint a very mathematical picture. Some lidars can reach, the lights can reach up to 12 meters. If you put this robot in a 3 by 3 by 3 room, that's 3 meters, 3 meters, and you keep it at the center, and let's assume there is no obstruction, empty room, just the robots, and you turn on this lidar, you would get the full map of the room just from one point. You don't even have to move the robots. The problem is if you now have an obstacle in front of the robots, if you don't move the robots will assume that this is where that room ends because the light cannot get to the other side. So you can have a lot of details on the other side and light will not get there. But what you can do is you can just like move the robot a bit. If I want the robot gets here, it's going to see everything that is on the other side. So it does not need to visit all the points. It just needs the light to travel as far as the next obstacle in sight. Chioke Destiny.
Okay, so good evening, everyone. Sorry,
Good
my
evening.
network has really been terrible. So even if I don't get what you said, I think that you do post the videos like about the meeting on YouTube. So I will
Yeah, I do
listen
record.
to them. Okay.
Okay.
So my question is now there is more to CAD, right? And
There is
I've
what?
heard um like there's more to that, just like I heard you mention about gazebo and all that, like you can simulate maybe what you designed and all that, right? Now, for me, that I am into CAD, right? And I'm kind of confused on the type of simulation I should use or I should learn or I should be good at, whether it's the structural type of simulation where we are talking about the structural analysis of the model, or the simulation, the motion simulation where you use the gazebo. So if someone wants to actually be good in robotics, should the person just focus on this type of simulation where you are doing just the motion study using gazebo? I don't know. I was still studying on
Okay.
the gazebo, or
So
what's the structural analysis and all that other simulations, because I just don't want to carry myself in a lot of work and all that.
okay, so your question is more like what should you focus on? Now I would give
Yes.
you 2 points of views, right? Um when I was doing my undergraduate, I did a lot of structural simulation. Now there's also thermal simulation, which is a different domain too. So for every if you know your robot is going to like gather up heat, right? You would also do thermal simulation. There were different simulations that we did back then. But from my point of view, I knew this because I've done them before. So when I saw software simulation, because mind you, what I just showed you is software simulation. It doesn't do any form of structure. It at most collision, but those impact tests, strength tests, no, it doesn't do that. So when I saw software simulation, like something like this, I was like, okay, yeah, this is what I want to do, because I'm someone that likes software from time. I preferred software rather than all the structure and things like that. So for me, that was my interest. So I went with that. Now I want to tell you why it's more like interest. There is no day that I regretted that I didn't do structure. Why? Because there is enough jobs in software, there's enough I can do. And I've never had to do structure, because the truth is, you're not being paid for knowing everything. If you know everything, it's fine. If there was a day where I had to survive on only just structures, I can easily fall back to that knowledge, but that's not something that is likely. Now I want to also give the perspective of Chidima's this thing. Almost all the training Chidima likes going for robotics. Even if I'm invited for free, I'm not going to go, because it's usually about the design of the robots. Not that I don't know design, I know enough design in order to apply it to my software, but there is no need for me to go intricately into design, right? So when she was talking, she was saying design of mounting LiDAR brackets. And she drew I saw the card up right here in our presentation. I was like, you mean this LiDAR bracket that we just toss in and screw onto the robot and we're done with our day? Somebody on the other hand is taking time to look at the structure to ensure that it holds up the LiDAR. She's still a robotics engineer. So what I would tell you is, this is more of a question of what do you like the most, what interests you the most, right? I cannot tell you do software simulation. I cannot tell you do structure. I can't tell you what to do. But what I would love to tell you is, if you pick one thing, right, ensure to do it very, very well, because at the end of the day, someone that knows something and is very good at that thing will stand more chance than someone that knows so many things, like shallow, right? You just pick from it, and like you just know all those many things. So that's what I would advise you. Then on Gazebo, we don't really do. If there is a plugin that even exists for structure, Gazebo is not for structure, right? So Gazebo is when you want to do, like you said, motion. You want to see how it moves. You want to keep, yes, you can do that, but there are things that will be for structures. Okay. Did I answer your question?
Yes, thank you very much.
Okay. So someone asked, what is the best way to learn CAD as a beginner, please? I have zero knowledge of CAD. What software can I use as a beginner? I think I would answer that from my perspective. I'll ask Chidima for our own perspective, so you get like a holistic view. For me, I started learning CAD with AutoCAD, simply because that's what was accessible to me. That's what I had, and I used YouTube. So I just search AutoCAD tutorials and I just follow what they do. Right? It's like what they do, I do. So like from there, I pick up what this tool is, and that kind of thing. And then from there, I moved to SolidWorks, and then I did CATIA, and then I did Rhino. So Chidima, is there any other thing you want to suggest to help stiffen out?
Okay, as a beginner, while it's important to start out with learning to draft, I would advise to use a software that is not too complex to learn, something like AutoCAD. But AutoCAD is limited to what you want to achieve, right? AutoCAD can only be used for drafting, like, depends on what you want to do. If you want to use CAD for proper products design, right? AutoCAD, Fusion 360, SolidWorks, they are very good options. But then, based on my preference and based on what I see that people do, and also from things like, let's say, job descriptions too, very important to note that you can actually use AutoCAD to learn to draft, then you can continue with Fusion as a beginner. Did that answer your question?
Yes, thank you.
Okay. As someone who is also interested in hardware aspect of robotics, are you saying having an intermediate to pro level mastery in software would suffice? And when does the line blur beyond the point of practical and interest? So first things first, right? What I normally do to my interns is I put them in different fields, right? One person doesn't start with software and do software forever. No, I shuffle it, I rotate it. I can shuffle and rotate for like 3 months, 4 months. The idea is you'll be the one that would even know what you want at the end of the day. By the time you try everything, right? There's so much knowledge out there that I don't know what you need for what. Now, there's a trick. When you've touched everything, you know what you like. Let us assume it's hardware that you like, and you go towards that. I'm coming to where it blurs the line between practicality and interest. Your interest now, you've picked CAD, or you've picked the hardware and you've gone into that. And practically speaking, you can make a career of that. You can make a career of that. And then you maybe get to a point where they tell you, maybe your boss is like, oh, and the current project needs some form of software. Now, because you've done software before, I believe since you've done everything on a basic level, you can always revisit and pick up. Now, I guarantee you, there is a profession called Jetson developer, where all they do is develop things that work on Jetson. Because if you've used an Arduino, an ESP, or you've used a Raspberry Pi, three of them are all different from each other, right? They are all different. They have their strengths and their abilities, but a Jetson it's like a laptop, right? It has its own ecosystem that is completely different, right? For the Raspberry Pi, you flash the SD card, you put it on the Raspberry Pi. The ESP, just plug it, you're good to go. Arduino, plug it, you're good to go. But the Jetson is setting it up alone is another form of university degree. So they are what they call Jetson developers. Up until November, I've never developed on a Jetson. And all I've been doing was purely robotic simulation, Gazebo, Isaac Sim, and things like this that I showed you. And I've been making good living off it, right? And then I suddenly saw a job that has to do with Jetson. And one thing about me is, I'll cut and come. So what happened was I ended up learning on the job. And I guarantee you, I think you should also find a way to understand that you have to learn on the job, because for a profession that moves as fast as robotics, the worst thing that you can do is to say, this is the knowledge I have and this is what I want to remain with. That's like the worst thing you can do. Even if you are picking up hardware, you are going to learn how to use newer hardware. And this newer hardware would also have their own learning curve, because hardwares are also different from each other. I literally have 2 robots from one company with one design ideology, and the two are very different on the software side. I'm not talking of, they all use ROS, they all use Linux, they use the basic stuff, the basic stack, but on how the software is architectured, it's completely different. So now I cannot say I'm on one side. You would have to learn on the job. You would have to pick and learn on the job. And unfortunately, your supervisors, they do not know that sometimes the stack required for you to do a particular job was not even on your CV. All they know is, oh, we have a robotics guy on the team. One time I was CC'd in an email that was sent to an OEM. An OEM is like a manufacturer of a robot. And in that email, I saw a paragraph where they said to reduce costs, the OEM, the company building the robot, should just assemble the robots mechanically and ship. That they have software people that will do it. Unfortunately, I am the software people that they have. The problem now is a bare robot will not run on ROS. You have to start from firmware. You would have to start building the lower layers upward before you can even, ROS is like on the higher level. And my domain is ROS. But your guys would assume that you know all the software stuff. Now, in a case where they've made that kind of mistake and now they've put the work on you, you are left with 2 choices. You either say, practically speaking, I cannot do this, and maybe they either have to hire somebody or maybe they sack you or whatever. But again, that's how crazy the world is. But I've never said I cannot do this. I can come and go down because I feel you should be dynamic as a human being wherever I find yourself. So yeah, that's like a summary of everything. Is CAD an application? I think CAD is a would I say it's CAD itself, computer aided design. It's just like mechanical design. It's a concept. Let me put it that way. The application is now SolidWorks, AutoCAD, CATIA, Rhino. Those are the ones that are under like softwares in CAD. But CAD on its own, there's no software that is called CAD. It's like a class of softwares. So I think I've answered all the questions for today. Yes, I've answered all the questions for today. All right, so today's slide was done by Chidima, right? So I am going to share the tags in a separate slide as alongside Chidima's slide too after this call. I want to appreciate you all for joining the call. I also want to apologize for the brief hijack of the call that we had to like fix, and people that were not on the call, I would also issue an apology and an explanation because it's really I think Google have been having a lot of issues this period because this is something that is I really don't know. All right, so thank you very much, and we'll see tomorrow being the last day of the webinar series. Good night, everybody.